Chapter 12, Section 3 starts with the ideal gas law, which is PV equals nRT. And in this problem, you're going to have P still being pressure, V with volume, N is still moles, T is still temperature, and the variable that's new here is R, which is a constant. There are two different R values that you can use depending on what units of pressure you're using. So if your pressure is in kilopascals, you'll use 8.314 liter kilopascals per mole Kelvin, or if your pressure units are in ATMs, you can use 0.0821 liter ATMs per mole Kelvin. So volume then has to always be in liters, N is moles, and then temperature always has to be in Kelvin. So here's a calculation for the ideal gas law. It says to calculate the volume of 1 mole of CO2 gas at STP. And remember, STP is standard temperature and pressure. So our known information is that we're trying to find volume, which will be in liters. We know that we're at STP, so we know that pressure has to be 1 atm and temperature has to be 273 Kelvin. Our moles was given as 1. And then since I chose to use the pressure as 1 atm, I'm going to use the R value as 0.0821 liter atms per mole Kelvin. I could have also chosen my pressure units in kilopascals. I could have made this 101.325 kilopascals. That's also standard pressure. But if that were the case, then I would have to use the other R value. So then I'm going to write out my equation, PV equals nRT, and then to solve our problem, we need to find volume. So we're going to have to take our moles, which is 1 mole, multiply that by our R, which is 0.0821 liter atms per mole Kelvin. Temperature is 273 Kelvin, and then we're going to divide all that by our pressure, which is 1 atm. So our atm units will cancel, our mole units will cancel, our Kelvin units will cancel, and all that's left over then would be our liter units. Another law that is discussed in this section is the combined gas law. Sometimes it's called the general gas law. And this one tells us that when moles remain constant, the other conditions can change. So it's kind of a combination of both Boyle's and Charles' law. So it's P1 V1 over T1 equals P2 V2 over T2. And here's a sample problem. It says a sample of CO2 gas occupies 45 liters. So there is V1 at 750 Kelvin, so there's T1, and 500 kilopascals, so that's P1. What is the volume? So we're looking for V2, which will be in liters, of this gas at STP. So standard temperature then is 273 Kelvin, and then standard pressure, since P1 is already in kilopascals, I'm going to go ahead and use standard pressure as 101.325 kilopascals. Then I'm going to write out my equation, P1 V1 over T1 equals P2 V2 over T2, and solve for V2. So I have to take P1 at 500 kilopascals, multiply it by V1 at 45 liters, and T2 as 273 Kelvin, and divide all that by T1, which is 750 Kelvin, and P2, which is 101.325 kilopascals. My pressure units and temperature units cancel, and all I'm left with are my volume units. Here's some gas stoichiometry, and what we're using here is Gay-Lussac's law of combining volumes. So basically what this does is it tells us that gas volumes can be determined from mole ratios in the balanced equation, or in this case volume ratios. So here's a balanced equation with hydrogen and nitrogen combining to make ammonia. So the 3 is then telling us that we've got 3 liters of hydrogen combining with 1 liter of nitrogen to make 2 liters of ammonia. And then I just made up a value here. I said if we had 22 liters of nitrogen, how many liters of hydrogen would we need to react with that? So you're going to use your ratio the same way we did with our mole ratios. So we want to cancel out our liters of nitrogen. So the 1 liter of nitrogen will go on the bottom of my conversion factor, and the 3 liters of hydrogen would go on the top. So my liters of nitrogen would cancel, and I could find out that I would need 66 liters of hydrogen to combine with the 22 liters of nitrogen. Okay, and I could set up the same type of ratio for finding how much of the product I could make. I would simply want to use the 2 liters of ammonia instead on top of my conversion factor.